This is the second video podcast for Chapter 11 on the ecohydrology of tidal wetlands. In the first one, I talked about what tides are and tried to provide some understanding of where they come from and how they vary around the world. And then I also looked in more detail at the hydrogeomorphic context of the estuaries and coastal zones where you find tidal wetlands. What I want to do now is go into the specifics of the processes that we find in the two most common types of coastal wetlands, which are salt marshes and then also tidal freshwater marshes. These provides the contrast between these two end member systems, and I'll define what those are in a few moments. So we're going to look into detail of these processes in terms of some geomorphic processes, hydrology, and even hydrodynamics, just following the hydrogeomorphic method approach. When you look at an estuary, and here is 3 maps of Chesapeake Bay, just for example, what you'll see is that there is a range of conditions in terms of the amount of salinity present. For example, in the map on the left showing the springtime condition, the red in this area indicates the oceanic high salinity that occurs with about 25 to 30 parts per thousand right at the mouth of Chesapeake Bay. So the bay has a very small mouth, and that's why there's a small red area. At the other end of the spectrum, all of the rivers that are pushing into the bay, bringing fresh water in, like the Susquehanna River and the Potomac River, for example, these are rivers that are bringing fresh water, and so they mix with the estuary and produce about 0 to 5 parts per thousand. During the spring, you have all the snowmelt runoff and your typical high spring flows associated with rainfall and snowmelt, and so as a result, you get this big push, what some people call like a freshet, where you're pushing that fresh water further into the estuary. As the year goes on, the seasons change and the salinity regime changes as well. And so by the time you get to the fall, it's a drier condition, and you can see that the saline conditions like this 15 to 20 parts per thousand has pushed in substantially farther, and the freshwater zone is quite limited. So you can have a geomorphic landform, like a coastal marsh that could be present anywhere throughout here. But as the year changes, it might switch back and forth between being salty, maybe intermediate, what we call brackish, or being freshwater. And so that makes it, the main criteria to distinguish here is the degree of salinity that predominates throughout the year, to put it into those categories. But there's a huge difference that we're confronted with when we talk about the hydrology of tidal marshes compared with the other landscapes we've looked at so far. And that is that most of the other landscapes we've looked at are relatively static compared to the dynamism, and I mean both how these systems change through time, as well as hydrologic dynamism, I suppose, of tidal marshes. So for example, think about a forest on a hillside. The hillside may experience some disturbances like fire and landslides, but that doesn't really change the topography dramatically in a short period of time. In contrast, we've seen phenomenal changes in the topography of wetlands in years to decades to even a few thousand years. And in fact, as I'll show you, most marshes that we see around the world today are only 4,000 years old. So in contrast, think about urban areas that are made impervious or rangelands. You can see changes in species and surface characteristics, but the actual landform itself is not really participating in the hydrologic dynamism. I think one exception would be, like highly breakable, what we call friable, geology associated in tropical, Central America, where you see like just massive slumping that's taking place, and large scale warping of landforms. But that isn't very common, and so we could treat that more like I'm trying to treat here. So with tidal wetlands, the point I'm trying to make is that when we think about the ecohydrology for this class, we have to think broadly. We have to think about hydrology as being an assemblage of allied disciplines ranging from how sediment moves and how nutrients are flowing, and then of course what the water balance is and the hydrodynamics. And so I'm going to be presenting much more dynamic material in this presentation than what I've presented before, because the other landscapes are relatively static. And just to illustrate that, in this slide here, I'm showing China Camp Salt Marsh here in San Francisco Bay. It's not that far from Davis. If you've never been, I encourage you to go and park here and then hike around some of these outcrops of uplands and get a view of the marsh. I take my class on a field trip here in other classes. And what I want you to see is that the majority of this marsh shows this one, brownish, greenish, military sort of color. And you see these channel networks that are moving through from the open water into the interior of the marsh. What you can see is that farther in, they're fairly meandering and dendritic patterns, but near the front, they're relatively straight. And there are these younger networks that are also quite straight. And one of the things that's really stark contrast is this brown material right at the front. And there's somewhat of a gradation in color from the darker color to a little bit more greenish olive and then to the brown. And what's happening here is that the system has grown quite dramatically since the time of hydraulic mining. So deforestation and hydraulic mining that took place in the Sierras delivered massive amounts of fine sediment to San Francisco Bay. And as a result of that, a lot of that material then was redistributed into the marshes. And this is just an example how within like 100-year time, we can see growth in the marshes and changes in the hydrogeomorphic functioning of the system. With the channel network changes, then the drainage is going to change, and the hydrology is going to change, and the vegetation is going to change. So there's a lot of dynamism that's at work, and I need to work through some of that in this video podcast. Another thing that's really important is the distribution of vegetation. Marshes tend to show a very strong zonation. Salt marshes tend to be very extreme because they tend to just have a few species and in quite a monoculture. In tidal freshwater, you don't have that salt pressure, so to speak. The plants only have to survive flooding, not necessarily be salt tolerant. And so we tend to find more zones, but here we have you go from the open water, which is permanently flooded, maybe a mud flat out front, which I don't have a picture of, and then you go to floating leaf kind of plants that the stems may be perennially inundated, and we'll talk about how they adapted to that condition in another lecture next time, chapter 12, I guess. To low marsh, then you get into the middle marsh and high marsh, which are quite distinct but have an assemblage of grasses and perennials. And then by the time you get up to the shrub, you're into well-drained sandier conditions where you can start to have shrubs and trees mixed in with the perennial and annual grasses, and then finally a forested condition where you have a denser canopy of taller trees. In addition to the natural dynamism that's present in these wetlands, there's also the fact that humans have fundamentally changed the landscape, and we've already looked at the impacts of human activities from an urbanization context, a deforestation context, but all of the water and sediment and nutrients that are generated from all of those changes in the uplands come down and change coastal marshes. And just picking on 3 examples, urbanization, deforestation, and intensive agriculture, those are really the big 3 in the standard United States context. But in other places, mining could be really big, or logging roads instead of just deforestation. Maybe it's more road issue. There are other impacts as well. These things tend to change hydrology, chemistry, and sediment. So I've color-coded those 3. And then those changes of what's coming down then has effects in terms of direct toxic impacts, changes to nutrients that create eutrophication and anoxia. But eutrophication then also works together with sediment to create turbidity and light limitation in the water column, which means then benthic organisms don't have a place to live. And then water and sediment together can change channels, can fill in estuaries, can grow wetlands where they didn't exist before. And I already showed you an example of that in one of the presentations. I'm trying to remember which one, but it's where I showed you the result from Frumer's study that showed the growth of tidal wetlands overstepping subestuaries. And then there are also hydraulic structures like dams, which create further flow modification. All of these things affect the hydrology and hydraulics What we talked about last time, the flow kinematics is another word like hydraulics. And then that can ultimately result in habitat conversion. So you go from an open water into an emerging condition. So if I step back one, this shows a spatial distribution that you can find in any one marsh, but this spatial distribution can actually be reflected through a temporal distribution, how something dynamically changes through time. And that's what's a little different from the forests and rangelands. There you don't have that temporal change so much as just spatial patterns. Here, something that's open water in short order can be filled in and turned into a riparian forest. And just to prove that that's true, we have evidence, for example, that many of the wetlands in the tidal freshwater zone of Chesapeake Bay, like if you dig down into the sediment, you'll come across the seeds of submerged aquatic vegetation. And this is a photo from an area that we think represents what much of the upper reaches of the Chesapeake Bay looked like before European colonization. And then here's a photo of those same areas as they look today. Now, it's during a flood, which doesn't, makes it even worse. But you can see, like, every time we have a high flow now, massive amounts of sediment are washing down from all of the urbanization, deforestation, and intensive agriculture. And you're taking an area that was once a lowland and turning it into a forest. And I'll show you more details of this as we go along. And it's really important to understand this context of dynamic landscapes before you even try to tackle the water balance. So for example, here's the place that I studied as part of my dissertation looking at watershed-estuary interactions. It's called Otter Point Creek, and this is a historic map from 1836. The green area is the area that I've highlighted that is illustrated having the characteristics of a delta. So even in 1836, there was already a delta that was prograding out into this Otter Point Creek. I put a star here in this one tributary called the Haha Branch that's coming in, and it's shown here using open water. So it's shown as essentially like a subestuary that would have had submerged aquatic vegetation. Then we go to the next stage, 1922, and what you can see here is that that green area has been overwhelmed by a much larger zone. So we've just gone, if I go back from 1836 to 1922, we're talking about 90 years or so. And you can see that the wetland has grown substantially in that time. Like the delta here is prograding out. And the Haha Branch hasn't really changed yet. And then by the time you go from 1922 to 1951, just 30 years, barely even 30 years, the wetland has grown again, and now it's overwhelmed the Haha Branch and is prograding farther out into Otter Point Creek. So going from the small green area to the red area, we're talking about growing an area by a factor of 7.5 in just 120 years. That's a really significant change. And you just think about what that means. How can you even talk about the hydrology of a wetland when it's changing that dynamically? I mean, that means that over a period of 5 to 10 years, you could actually watch this site change, if conditions, continue to grow like that. Okay, so let's look at the water balance for a setting like this. I mean, this is the same exact place. And now if I just put it into a water balance context, I mean, here we're bounded because we have these roads that are cutting in, and you have the uplands that are indicated by the urban developments on both sides. So the wetland is here in the middle, and we could pretty much just draw a control volume about that. We could identify streams that are discharging into the system as Q in, and there's this major one, there's a minor one here, and then there's the Haha Branch one that's in between. We have the gross precipitation that's just falling right down on the land. You've got evapotranspiration from the the vegetation, ponds, and then the tidal front. And then you have TE here, just is tidal exchange. That is that over one tidal cycle, starting at mean water level, going to high tide, down to low tide, and back up to mean water level again, you have a tidal exchange. And then on top of that tidal exchange, the fact is that the river is pumping water in, and so that water has to go out. So if you were to assume that the tides are coming in and out with like a net of zero change, then we can have a term of net non-tidal flow being the water that's coming in from stream flow or being removed out of storage from the wetland and fluxing out. So you can see this is a significantly more complicated water balance to deal with, even if you treat the thing as a static system. You're pretty familiar with a lot of the sensors we've already been talking about, but tidal exchange is highly dynamic. It's extremely hard and labor intensive to monitor, and that makes it very difficult. Let's take a look at what water level conditions look like in a tidal wetland. And obviously, there's an assignment for the class that uses this data, and so you can get a feel from that. But just from this context here, you can see that tidal level in an open channel is, in this case, semi-diurnal. I've indicated some of the spring and neap tides. You don't really see that. Notice that it's not a simple tidal signal like was shown in the part 1 of chapter 11. You can't really see, here we're going over more than a month. You can't really clearly see spring and neap tides at all. Here's like full moon and new moon. There happens to be a bigger event here, but it's just one day. It's not part of a periodic cycle that's modulating. So there's a lot of other processes that must be taking place, and that's one of the things that makes wetlands complex, because you have stream flow, you have tides, and you have winds that are all impacting it. Now let's move on to the marsh surface. It's the same time frame, but instead of being in the channel, now we're on the area designated as the high marsh. And so whereas the open channel, you see the full swings of the tidal cycle, on the high marsh that gets abated because there's basically just saturated conditions that are present. So you have essentially zero to just a little bit of water. And then every time the water spikes, that the elevation of the water rises above the high marsh, then you get that inundation. But that inundation is highly uneven. Like, this doesn't even look like a tidal signal compared to what you saw in open water. And the open water was already pretty ugly looking. We could also take this data, which is also part of an assignment that is associated with the class, and you can plot what's called the non-exceedence probability. This shows how frequently water levels of different elevations occur. So if we say here, take 0.5 and go across, let's just pretend that it hits at 5. What this means is that only 5% of the time does water level not exceed this stage of 0.5 feet. That means that 95% of the time the water does exceed that. Also notice that the x-axis here has a very strange configuration of numbers. That's because this is called probability paper, and it's designed so that the normal distribution will fit as a straight line. So if we were to attempt to fit a straight line, it sure looks like from about 10% to 99%, you could fit a straight line, but then it deviates from normal at the tails. And that probably means it's some kind of log normal distribution with very rare, well, I mean, with these rarer conditions, behaving differently. Now, that totally changes for the high marsh, because the high marsh is dry. So like, 70, let's go to here, like 80% of the time, the water level barely exceeds 0.2 feet. Whereas here, 1/10 of 1% of the time is at that level. So the high marsh is way drier. The median condition here is dry. The median condition here is pretty wet. So this kind of plot is a very compact, convenient way of looking at the totality of water levels that occur, different from looking at the time series. You can get the same idea from a time series, but this is much more of a head-to-head comparison of the totality of the occurrences of different water levels. Let's look conceptually at how the hydrology of a marsh works with tidal fluxes that are coming in. What's actually happening? So in this map, on the left, you see a tidal channel. There's little waves here. And then you go from inside the tidal channel to the shoreline, and then up a levee, or the bank of the channel, and then out dipping down into the marsh. So there are 5 locations as you go from the channel away, and each one we're moving a few meters away, basically. So if you start at low tide, the marsh is saturated pretty well, but the channel is low. And that means that water is going to be flowing from the high elevation to the low elevation of the water surface. Like water always flows from, its potential energy, like high elevation water to low elevation water, when you just have this kind of, hydrostatic end members. And so that's why the arrows are oriented out. Now you go from the map A to map B, and now the tide is rising. As the tide is rising, it's filling in, and we can see that the area, you have two processes occurring. The shoreline is filling in, so the shoreline is actually getting wetter, but meanwhile, drainage is still occurring from farther away. So those two are meeting head-on at some point, which is shown where these two arrows meet. And then at C, we've pretty much inundated the whole thing, and there may be still a pocket of dry soil conditions that's smaller, but then those are meeting. If we look at this through time, so this is time now. This is not a channel shown here. This is not a channel. This is through time. So we start in the channel, which is the solid line, and in the channel we see the tides going down and then the tides going back up again. If we move a little distance away, let's see, so we go from 1 to 2, that's 2 meters away. So you can see that we're 2 meters away from the channel. The response is still very similar. It's, there's a slight difference. As you get to point 3, which is now 4 meters away, you start to see some mitigation. So we're high enough now that the water level is not dropping all the way down. It's staying saturated. And then the water level in the channel comes up and floods it out again, and then everything is flooded. And let's just zoom out. By the time you get to point 5, you're at 4, 6, and 4, 10 meters away from the channel. You can see that point 5 is not inundated. It's flat for long periods of time. Then eventually the tide reaches that and it inundates. And that's exactly what we're seeing in this plot here, that you have these long periods of time with no inundation, while the tide is changing in the channel, but it's not reaching this elevation. So hopefully these plots give you a sense of how that flooding works, that the channel, the tides are going up and down, but any one location in a wetland may not receive that tidal exchange depending on its elevation. Now it gets more complicated, and see, this is why we have to build this up from the ground up. So that's just the tidal signal. Okay, but it's very important to understand, like in chapter 1, I tried to convince you that, the moon and the sun, we had these tidal effects, and they created these periodicities. But remember, even there, when I showed you the harmonic analysis, there was always a residual. After you subtracted all the periodic functions, there was a residual outcome where there was still water level variations that couldn't be explained. And when you look at this open water signal, it's very prominent. And you'll see that in the assignment when you process that data. How come some days there are no tides? That's the key question. And it's actually a question that you have as a homework question. And this pretty much is going to address that. Well, the important way that I can explain this is, let's switch to music, because music is no different than water level variations. You know that every time you push one key on a piano, you get a signal, and it's a frequency signal, and it would look like like a sine curve to a rough extent. It has a frequency, and the reason why one note sounds different from another note is because you've made a change to the frequency of that sound, by affecting a string or whatever the mechanism is for the instrument that you have. I used to play trombone. You tighten your lips differently, and you could create a different note. Now, when you play a piano, if you press 2 keys at the same time, you're going to hear both keys, but they're occurring at different frequencies. Now you're asking yourself, what the heck is this guy talking about? I mean, now we're talking about music. What does this have to do with anything that we're seeing? Well, what it has to do with is that tidal records have different frequencies that are occurring all at the same time. Now, no one is more important than no other necessarily, but they're all occurring at the same time. How can I know that? Well, here's a wetland known as the Atchafalaya River and its delta. And you can see the delta that's growing out in this map. Well, there was a study done in which they monitored the water levels, and then they took the water levels and they averaged them to different intervals. So if you take the data and you plot the monthly water levels over many years. Here we are going 1979, 80, what's the 7 years or so of data. The water levels are shown as the dashed line. And then the solid line shows the flow from the Atchafalaya River. And you can see that these wiggles roughly line up. Like when flow goes up, the water level goes up. When flow goes down, water level goes down. So on a monthly to annual to interannual time frame, water levels are responding to discharge. However, if you take the exact same data and average it to get the daily signal instead of the monthly signal, and then you compare it to wind speed, or in this case, wind stress. Don't worry about how we calculate wind stress, but it's basically proportional to wind speed. There's a directionality to the wind speed, and so when the wind speed is blowing in one direction, like pushing in, the water level goes up when wind stress is directed this way. When the wind goes down, and the wind is the solid line, and the water level again is a dashed line, the water level goes down. And if the wind reverses, like here it's now, negative wind means it's blowing in a different direction. So like when wind is pushing the water out, then water level goes down. So you see there's two processes occurring at the exact same time. In the same way that if I press two keys on the piano, you will hear the low note and the high note at the same time. Here in the wetland, you see these signals at the same time, but they're not interacting with each other. They're both there, and you can average the data to see each process, but it doesn't necessarily mean that one is more important than another. So how this plays out is if you try to do a water balance and you just measure wind stress, for example, then you're going to, if you monitor over a period of a few hours to a few days, maybe the river discharge didn't matter. Like maybe you spend thousands of dollars measuring river discharge and you forgot to measure wind stress. If you want to look at short-term fluctuations of water level in a wetland, in a tidal wetland, you have to factor in winds. You can do tides, but you have to do winds. If you want to look at seasonal to interannual timescales, then you just have to set up your design that you're going to be able to cancel out wind effects that are relatively short term and see the underlying monthly river flow signals such as shown here. So this is a complex slide. I mean, I've spent a huge amount of time trying to explain this, but it's very, very important in the tidal hydrology context. Okay, this is now looking at it in another way. If we go back to this data here, so this is your time series of water level. Some of you may know, like if you've taken enough mathematics, that you can take this data and calculate the frequency of components of this signal. So like the semi-diurnal tide has a frequency of once every 12 hours. The diurnal tide has a frequency of once every 24 hours. So you can take a whole time series and get one number from that, and that's the characteristic frequency. Well, there's an analysis called Fourier Analysis that allows you to see the whole distribution of those. I've already showed you a little bit about harmonic analysis, which allows you to extract the individual frequencies, while Fourier Analysis just shows you that distribution. So first, just look on this axis going across the screen, what I'm going to call the x-axis. It has a frequency in how many times per day something occurs. So once a day would be a diurnal signal, and then if we go to half of that, that would be twice a day. 1, 2, 3, 4, 5. So that would be something like here. Oh wait, no, that would be, I'm sorry, I went the wrong way. Twice a day would be 2 times a day, that would be here. Okay, so now here's the interesting thing. When you have something that is very dynamic and doesn't purely respond to just a periodic signal, like tides just rise and fall once or twice a day, or the earth heats and cools, day, night, day, night. When you have something like wind, and this is a wind plot, then it changes more dynamically through time. So if we just look at this one little graph at the very front here from 1995, what you can see is what is the frequency structure of the wind signal. Twice a day, there's just a tiny little blip there. There's definitely a diurnal cycle once a day. That's like heating and cooling. But you could also see that winds have these variations that range from once every 3 days to once every 7 days. And so the higher this is, that means the more persistent the variation is occurring at that frequency. So what I can do then is I can project that through time and say, okay, well, for a 2-week period at the beginning of 1995, here's the structure. And now we shift down through the weeks and we can see how that changes. And what you can see is that there is a persistent diurnal cycle as we move through time that's in the data. But you can also see that there's way more action taking place in winds in this 3 to 7 day period. In this first 20 weeks of 1995, there's a very strong differentiation between like a 3-day and 7-day. But by the time you get to the 20 weeks, you head from like, late spring into the summer. There's 52 weeks in the year, so halfway is like what, like 26 or so. So middle of the summer, those have all coalesced into one thing, like right in that mid-domain. And then it grows and grows again, so there's a modulation that's taking place. And then you get to 1996. And then boom, we're back to two clearly differentiated peaks. Okay, wow, I'm showing you a lot of new stuff. I bet a lot of you, this could even be the very first time you've ever even seen a frequency distribution in a Fourier analysis, and I've tortured you by putting it as something that varies through time. So let me just back up again and just emphasize this. You start with a tidal signal and you say, why is this here? Why do the water levels go up and down the way they do? And then you say to yourself, well, gee, I think it has something to do with the river discharge. I think it has something to do with the tides. I think it has something to do with the winds. So then you can start doing some averaging and you can say, you know what? This wiggle sort of matches up with that wiggle and these wiggles match up with those. I'm seeing some effects. And then you can turn on your math skills and go even further and do a Fourier analysis. And this is something you can do in Excel. Is something that you can do using MATLAB or R or a variety of approaches. There's some pretty standard scripts that do this analysis. So you can take any time series, if you've sampled it uniformly through time and you fill in holes or whatever's there, you can analyze it to see what are the key frequencies that dominate that system on average, and then how those can vary through time. And what this is showing is that wind, it definitely shows persistent diurnal effects and persistent variations in the 3 to 7 day period. But those variations in the 3 to 7 day period are dynamic. They change with the seasons, and they even change as a function of longer term climate phenomenon, but I'm not going to go into that. So you could see that compared to the water balance in a forest, urban, all those were like piece of cake. Now let's get into a very dynamic environment. Now we're in a different world. We're in wetlands. We're in floodplains. All bets are off. And what's nice about wetlands, they do have a persistent tidal signal that does help to make it easier. But when you throw in the winds and river flows, it gets messy quickly. And this then takes it to even one more level. Just like how we can make a correlation. So this shows the correlation between, well, it doesn't show a correlation, but you could take these two levels, and in Excel you could go equals coral and calculate the correlation between these two. Or you could make a scatter plot and fit a line to it and calculate the R² value. You're all very comfortable with that. Well, now we've got frequencies, and we'd like to know, does the structure of the winds and how its frequencies change, are those correlated with the frequencies of water level changes? So let's just look at this top plot. What this top plot shows is that that the y-axis here is r², so that's correlation as you know it. But instead of just having one value like in a scatter plot, here on the x-axis we have the frequency. with a frequency like 1 being once a day, and then less being occurring less frequently than once a day. And at the top, I'm giving those periodicities, which are going 1 and 1.25 days, 2, 3, 5, and 7 days. So what this is showing is the correlation between winds and water levels in a tidal wetland using R squared, the coefficient of determination. And it shows that you don't just correlate winds and water levels like, oh, they're correlated. Oh, one controls the other. Like when we do rain and discharge, okay, rain comes and it controls discharge. It's actually more complicated than that, but it's very tractable. You just have to calculate what we call the coherence. Coherence is the correlation in the frequency domain. This isn't something I'm going to expect you to do in this class, but I'm just trying to show you, I'm trying to open your mind to more interesting ways of looking at hydrology. And coherence is really cool and really powerful. It shows us the correlation of each frequency in the data. So you have noisy data. You're all going to end up in your life with noisy data. And you say, well, I think this has some control over that. Instead of just doing a correlation in the time domain, you can do a coherence analysis in the frequency domain and find those correlations. And you can see the biggest correlation overall is a 7-day cycle. Water levels and winds are fluctuating together at a 7-day periodicity. There are also very strong like 2 to 3 day periodicities, but pretty much the whole block from 1 2/3 days to 7 days are all correlated greater than 0, R squared greater than 0.4. So these are actually, that's the cutoff for my analysis here where it's statistically significant. So we have some very strong statistically significant correlations, and certainly winds and water levels are both fluctuating on diurnal cycles. How do we know that the winds are actually pushing the water levels in this tidal marsh? To do that, you have to look at which one comes first. So here I've shown three time series: black, blue, and red. So look at the black one. The black one is going up and down and then up again. Now look at the blue one. If you look at the blue one, you can see the blue is going down first, and then hours later, the black one goes down. Then the blue one goes up. Hours later, the black one goes up. So they might be linked together, where the blue one's happening first, and then it's driving the black one. Similarly, the red one goes up first, and then the blue one goes up. So like maybe the red could be winds are blowing, and then later on, water levels in blue are going up. So like red to blue is a very short period of change or lag, and then blue to black is a very long lag. On the other hand, in this case, like red and black are exactly opposed. If two things are happening either right on top of each other at the same time or in opposites at the same time, one really can't be driving the other. It's very unlikely that to have no lag at all. It's more likely that some third process is causing both of them to happen. So there's an analysis called cross-phase analysis, and what it does is it looks at each one of these frequencies and it tests whether there's a lag and who's driving what. And what I can tell you is that in this case with these negative numbers, anytime that this is a negative number, it means in this case that wind is driving water level change. The fact that it's really noisy over here, it doesn't mean anything because there's no correlation, so I'd pretty much forget that. But here you can just focus on the fact that for these effects that we're seeing in the 2 to 7 day period, winds are occurring and they're driving fluctuations in the water levels. The one cautious thing I would note about this analysis, it's so powerful that it can see any small fluctuation that one process is causing to another. It doesn't tell you anything about how big of an effect it is. It doesn't tell you, oh, the water level is changing 10 feet. Like this very strong correlation, it could be a very small effect. Maybe it's like 2 or 3 centimeters of change. Who knows? We just know that they're very tightly correlated and one is driving the other. So I've had to go into a lot of detail to explain these processes because we're talking about what is the water balance in a wetland. It's going to be driven by tidal exchange, but in a key part of that wasn't on that plot, it's kind of tricky, But this plot here, this does not include winds at all. But winds, you can really think of it as part of this tidal exchange, because winds are pushing water, creating water level fluctuations, and it does include both periodic and non-periodic components. Another thing I can show you is that when you have high winds together with low water depths, then those winds can really be pushing on the bottom of the wetland. So if you have a little bit of inundation and you get winds, that's creating very high velocities, and then that creates high shear stress. Shear stress is force per unit area. It's like a pressure, and it's the force that's imposed on the riverbed per unit area that can stir it up and pick up sediment, and then the winds can carry it in whatever direction the tides are going. So we can drive landform change as well as have water level fluctuations from wind speed. I think I'm going to skip this. It's just going into it, showing the time series of that, and leave it there. And so the bottom line is, what I've tried to convey is that when you want to do a water balance in a tidal marsh, you can set out your precipitation gauge, you can set out your stream gauge, but you better pay attention to tidal exchange and winds. You better be pretty darn sure, make sure you have a wind sensor and you're measuring it, at a very high frequency so that you can count for that. And then something like a frequency analysis may be needed, so a more sophisticated analysis to see those effects.